Waveguides, Hollow Pipe Waveguides, series on Microwave Engineering, lecture number 1.00. Hollow pipe waveguides are capable of carrying high frequency waves or signals from one point to another point without radiation losses. They carry the wave in non-TEM form. Under hollow pipe waveguides, we study three configurations: parallel plate guides, rectangular waveguides, and circular waveguides. In the present session, the focus is on various common features that exist in the behavior of these three types of hollow pipe waveguides. Cylindrical waveguides. Hollow pipe waveguides are called cylindrical waveguides when their cross section is uniform throughout its length. The cross section can be rectangular, it can be circular, or it can be some other shape, but the requirement is it must be uniform. So rectangular waveguides are cylindrical waveguides. Circular waveguides are cylindrical waveguides. Waveguides serve the purpose similar to that of transmission lines, transfer of signal from one point to another point. Mainly, they are used at microwave frequencies 3 to 100 gigahertz. At these frequencies, for larger distances, hollow pipe waveguides and coaxial lines are used. For smaller distances, dielectric slab waveguides, IC microstrip lines are used. Hollow pipe waveguides are basically hollow conducting metallic pipes. These are single conductor systems. These are 2 points that describe most of the hollow pipe waveguide system. George Southworth and Barrow invented waveguides independently in 1930s. Before that, earlier to 1930s, in 1893 itself, Heaviside considered the possibility of propagation of wave inside closed hollow tube, and Lord Rayleigh later proved mathematically the possibility. They support TE or TM waves, that is non-TEM waves. Basic difference between a transmission line and waveguide is transmission line is a TEM medium, whereas waveguide is hollow pipe waveguide is non-TEM medium. They have dimensions that are convenient only when frequency of operation is 300 gigahertz. If you try to design a waveguide that can carry frequency which is more than 100, the dimensions become too small. The dimensions of the waveguide become too small. If you try to design a waveguide that can transmit frequencies below 3 gigahertz, the dimensions of the guide becomes too large to handle comfortably. So only when wave frequency is between 300 and 100 gigahertz, the dimensions of the guide, they are comfortable to handle with. Waveguide can be considered broadly as consisting of two regions: highly conducting outside walls and almost non-conducting inside hollow region, which is usually free space. Sometimes a dielectric may also be filled, but most of the times it is air. Both of these two regions have important roles in transferring the signal. The wave travels through the waveguide, filling the dielectric, not by the conductor, not by conducting along the guide walls. So this is waveguide. Let us say this is waveguide. These are side walls. Wave actually it doesn't travel straight from source to the load destination. Its journey is like this. It goes like at an angle, hits the wall, gets reflected, travels, reaches another wall, hits, gets reflected, again travels to the other wall. Like this, in a zigzag path, it keep on. It travels from one side to one end to another end. Notice in this process of heating and reflection, the wave is most of the times in the dielectric region. It is touching momentarily, only momentarily, the walls. So the wave travels through the waveguide, filling the dielectric, not by conducting along the guide walls. Actual signal transmission involves multiple reflections. As already mentioned, reflections from the walls into the dielectric. It is the hollow region through which wave actually travels, and purpose of the walls is just to confine the wave to the hollow region. Waveguides and coaxial lines, they are contending each other at least over certain portion of microwave region. Their relative merits and shortcomings are needed to be mentioned. Note, coaxial lines are also capable of carrying microwave signal, microwave frequencies, and waveguides there also. So both are there, both can be used most of the times. What are their merits, relative merits and demerits? At lower end of microwave region, apart from waveguides, coaxial lines are also used at high frequencies. At the lower end, both waveguides and coaxial lines are okay. Both can be used in applications at the lower end of microwave range. Waveguides have the advantage of higher power handling capability and lower losses, mechanical simplicity, easy to manufacture, less likelihood of flashover, higher maximum operating frequency. In other words, what he is telling is, at the lower end of microwave region, you can use coaxial lines, you can use waveguides also, but the thing is, waveguides have an edge at this range. That is with respect to power handling capability, with respect to losses, with respect to flashover, less likelihood of flashover. These are all advantages when you use waveguides. Of course, at higher end of the microwave range, waveguides are only the possible medium. When compared to coaxial lines, guides are inflexible. Relative certain demerits are also there as far as waveguides are concerned. Coaxial lines are flexible, whereas guides are inflexible. They are bulky, they are expensive. Coaxial lines, on the other hand, have very large bandwidth and very convenient even for test applications. Lower maximum operating frequency, that is 18 GHz, and difficulty in fabricating complex microwave components are two major disadvantages with coaxial lines. So, maximum operating frequency, it is only up to 18 GHz. That's what it is being told. Only they are okay on the lower or lower microwave range. Certain difficulties are also there in fabricating microwave components using coaxial cables. Now, certain important points. Waveguides are cylindrical when their cross section is uniform throughout its length. When the cross section is rectangular, they are rectangular waveguides. When it is circular, they are circular waveguides. Several cross sections are possible, but rectangular and circular ones are the cross sections that are widely used. Various cross sections that are possible are, this is rectangular, this is also, this is square, this is circle, this is ellipse kind of thing, this is a H. So like this, different kinds of possible, but the thing is only rectangular and circular. A and D are widely used. Why others are not preferred? One reason is analysis of these structures are quite difficult. That's why they are not used. Waveguides versus transmission lines. A comparison between transmission line and waveguides. Reason for comparison is both are used to transmit the signal from one point to another point. Purpose is same. Both serve the same purpose. So naturally, a comparison is required. A comparison helps to understand their nature. Waveguides are single conductor systems, whereas transmission lines are multi-conductor systems. Energy travels in the form of TE, TM or hybrid modes in waveguides, non-TEM mode, whereas for transmission lines, it is always TEM. Cutoff frequency. The wave frequency must be larger than certain value known as cutoff frequency in order to propagate through the waveguide. In other words, what he is trying to tell is waveguides are high-pass filters. They allow the wave to pass through them only when frequency of the wave is more than certain value, which is known as cutoff frequency. Whereas transmission lines are no filter nature, no filtering nature. All frequencies, 0 onwards up to infinity, any frequency can be transmitted over the transmission line. Modal propagation is an important and a special feature of energy transfer through waveguides, whereas field distribution in transmission lines is non-modal. Signal journey through waveguides is in the form of modes, which is not the case in case of transmission lines. In addition to that, several differences are there between waveguides and transmission lines. These are all enumerated here. Hollow pipe waveguides, analysis is done in electric and magnetic fields. Here analysis is in terms of voltages and currents. These are single conductor, these are multi-conductor, these are dispersive. Dispersive means properties changing, particularly velocity, changing with frequency and wavelength. It is non-dispersive. Velocity of the wave over the line is same whether it is low frequency or high frequency. Here it is non-TEM wave. Here it is TEM wave. Non-zero cutoff frequency. Not all frequencies are allowed. Only frequencies which are more than certain value called cutoff frequency are allowed to propagate through them. Here modal propagation. Whereas here cutoff frequency is 0, propagation is non-modal. This is a diagram giving a comparative description of hollow pipe waveguides with transmission lines. Analysis of waveguides. Analysis is similar in all the three types of guides which are under consideration. That is, hollow pipe waveguides, rectangular waveguides, circular waveguides. In the analysis of each one, certain steps are there. These steps are common among all the three structures. In the analysis, what we do is we try to find out fields inside. We try to estimate or find filter characteristics. We try to find modal propagation characteristics. We try to estimate dispersion characteristics. We try to find out impedance nature. We try to find out attenuation. See, when wave is traveling through the guide, wave means it is electromagnetic wave, so it is involved with electric vector, magnetic vector. What is E? What is H? Finding fields inside means when wave is traveling through the waveguide, what is E? What is H at an arbitrary point inside the guide? Filter characteristics. As already mentioned, guides are high-pass filters. What is the cutoff frequency? It is our cutoff wavelength. That is main aspect which we investigate under filter characteristics. Modal propagation characteristics. While traveling through the guide, wave possesses certain amount of structure with certain features. These structural features, they are discussed or they are found under modal propagation characteristics. Dispersion characteristics. Waveguide is, hollow pipe waveguides are dispersive in nature. Velocity, impedance, etc. all change with the frequency or wavelength. So their behavior is dependent upon frequency or wavelength. That particular aspect is studied under dispersion characteristics. Impedance properties. The two types of impedances are there, wave impedance and characteristic impedance. When it comes to waveguides, those two impedances are studied and their expressions for them are derived. Attenuation characteristics. While wave is traveling through the guide, it comes in contact with walls of the guide, as well as we have already seen most of the time it is in the dielectric medium. If the dielectric is a perfect dielectric and if the walls are made with perfect conductors, then the wave travel is without any attenuation. But when walls and dielectric are not perfect, then certain amount of energy of the wave is absorbed by these two agencies, resulting in wave attenuation. That particular aspect is studied under attenuation characteristics. These are common aspects pertaining in all the three guiding systems. In all the cases, analysis is done in phasor domain. Wave is assumed to be traveling in positive z direction. Guide is assumed to be very long, preventing possibility of reflected wave. So, in the analysis, we do the analysis in phasor domain and we assume only single wave is traveling, no reflected wave or no standing waves. Analysis steps. These are common. As I already mentioned, these are common to all the three configurations. Walls are assumed made with perfect conductors. This assumption makes the analysis simple. Hollow region is assumed to be a perfect dielectric. So wave is traveling without any attenuation. Now waveguide is similar to a lossless line. Attenuation is not there, therefore attenuation constant is 0. Wave travels without any attenuation. When attenuation is 0, attenuation constant is 0, propagation constant is pure imaginary quantity. All these assumptions, they are made even though these assumptions make the guide under consideration far from the practical guide. These assumptions make the analysis simple. Once assuming this ideal nature, once we complete the analysis, after the analysis is over, completed, then we consider practical or real situation to amend the results that are obtained with ideal conditions. Propagation constant is an important parameter. It is a complex quantity in general. Real part is attenuation constant, imaginary part is phase shift constant. Alpha represents the attenuation the wave undergoes and imaginary part beta represents phase shift constant, denoting phase change in wave motion. In the analysis, loss-free conditions are assumed and hence it is an unattenuated wave transmission with pure imaginary propagation constant, gamma equal to j beta. The bar over the symbols indicates that they refer to non-TEM waves. Finding fields inside the guide, it is done. It's a long process involving several steps. It is complex also. So one can divide it into two parts. First part is expressing transverse components in terms of longitudinal ones using Maxwell's curl equations. In the second part, longitudinal components are found using wave equation. Once longitudinal components are available in the second part, they are taken and substituted in the expressions where transverse components are in longitudinal ones. Now we have transverse components of the fields. Anyway, we have calculated longitudinal components in the second part. Now all the field components are available. That ends the process of finding fields inside the guide. First part starts with defining problem by specifying constitutive parameters sigma, mu, epsilon and the structure. Then we have to select appropriate coordinate system. In the analysis of rectangular waveguides and parallel plate waveguides, Cartesian system is the appropriate one because they involve rectangular symmetry. When we do analysis of circular waveguide, we use, and it is appropriate to use, cylindrical coordinate system because circular waveguides, they have cylindrical symmetry. So it depends upon the symmetry exhibited by the structure. Then we consider Maxwell's curl equations. What are Maxwell's curl equations? One is Ampere-Maxwell's law, another is Faraday's law, and they are expanded to get two sets. A total of 6 component equations. One curl equation gives 3 component equations. Another curl equation gives another 3 component equations. Total, we get 6 components. Selecting one from each set, relations for transverse components in terms of longitudinal ones can be derived. They are derived. Now, before going further, a brief regarding EM waves. Several types of EM waves are there broadly, and relevant division here is into TEM waves, non-TEM waves. In TEM waves, you have plane waves, cylindrical waves, spherical waves, non-TEM waves. TEM waves you can find in transmission lines and parallel wire transmission lines and free space, coaxial lines and all that you can find. Non-TEM. We are in waveguides. Waveguides they carry non-TEM waves. What are non-TEM waves? Longitudinal component of either E or H or both exists. Neither E nor H is entirely transverse. These are dispersive in nature. Hollow pipe waveguides, which are under consideration right now, they hold non-TEM waves. 3 types of non-TEM waves are there. One is TE. E is entirely transverse and H has a longitudinal component, that is TE. TM wave, what is TM wave? H is entirely transverse and E has a longitudinal component. Third type is TE plus TM. Another names are also there like mixed waves, hybrid waves. Both E and H have longitudinal components. In simple terms, I can tell what is TE, what is TM. TE, wave is traveling like this, let us say, Z direction. TE means electric vector is perpendicular. So component of electric vector parallel to direction of propagation is 0. And H usually it is like this. It can be like this also. Entirely parallel to direction of propagation also. E is entirely transverse. H is having a component along direction of propagation. This is TE. If roles of E and H interchange, then it becomes TM. In TE plus TM, what happens is E is like this. H also will be like this. Both E and H are having a component parallel to direction of propagation. EM waves, as already mentioned, can be divided into 4 categories. TEM, transverse electromagnetic wave, TM, TE, TM plus TE. In this part, it can be found TEM waves cannot exist in cylindrical guides. So, we don't discuss much about TEM waves. To have an understanding, TEM means electric vector is entirely perpendicular, magnetic vector also entirely perpendicular. Both are entirely transverse. Then that is TEM. In case of non-TEM, one or both, electric vector or magnetic vector or both, must have a component parallel to direction of propagation. In part 2, that is part 1, in part 2, what we do is longitudinal components are estimated. We consider wave equation for a longitudinal component. We solve it First we get general solution. It is obtained using a special technique. It is known as variable separable method. Wave equation is not an ordinary simple common equation. It is quite complex. It is three-dimensional, or in the present case it becomes two-dimensional, second order equation. Getting solution to such equation is not an easy task. A special technique is applied. The name of the technique, as already mentioned, is variable separable method. When this method is applied, wave equation gets split into two equations, two simpler equations for which solutions are available. So now we obtain general solution. We have general solution. General solution involves certain arbitrary constants. Values to these constants requires to be fixed. To fix them, boundary conditions are required. Boundary conditions, using boundary conditions, values of arbitrary constants are fixed. And boundary conditions, these are not given. These do not come from skies. We have to derive on our own. Mostly these are based on one of the boundary conditions, which says tangential component of electric field must be continuous across the interface of any two different media. From that boundary condition, the boundary conditions that are relevant in the present situation, they are derived. One can start with wave equation for some other any component also for which boundary conditions are available. Say wave equation for actually we started this slide with the statement wave equation for a longitudinal component. We start with wave equation for a longitudinal component. Let us say this longitudinal component doesn't have any boundary conditions. Then you can have general solution, but what we want is particular solution. To reach particular solution, we need to have boundary conditions. Let us suppose boundary conditions are not available to the component which we are considering. Then you get brakes applied at this point. So what he is telling is, instead of longitudinal component, you can consider any other component also. No problem. Consider for which boundary conditions are available and proceed and apply the procedural steps that are mentioned here. Okay. First we assume wave is TEM. TEM means Hz is 0, Ez is found with the help of wave equation. Then we assume the wave TE. So Ez is 0, Hz is found by applying wave equation. Then we assume the wave as a hybrid. Ez and Hz both are found by the help of wave equation. Once Hz, Ez are available, of course we can use the relations we derived connecting longitudinal components with transverse components to find transverse components. Okay. With the availability of longitudinal components in part 2, with the availability of transverse components in part 1, total field components now can be said to have available. To find fields from wave equations, boundary conditions are required, as already mentioned. They are derived from a statement in field theory which says tangential electric field at the surface of a superconductor is 0. Filter characteristics are, as already mentioned, waveguides behave like a high-pass filter. There is a cutoff frequency, a cutoff wavelength. When frequency is lower than cutoff frequency, wave is not allowed to enter. Frequency of the wave must be more than cutoff frequency. Cutoff wavelength is wavelength corresponding to cutoff frequency. Their values are dependent upon several parameters like dimensions, modes, and all that. In this section, relations for cutoff frequency and wavelength are derived. Modal propagation. Waves in guides travel with definite structures called modes. Several different modes are possible. Out of all, only some are useful. This structure is specified by transverse nature with mode numbers. The physical meaning and implications of these modes are studied in this particular section. Under dispersion characteristics, we study the frequency dependence nature of waveguide. Velocity is variable with frequency in waveguides as they are dispersive. Even impedances attenuation also change with frequency. Expression for guide wavelength, expression for phase velocity, expression for group velocity. All these are derived under dispersion characteristics. Two types of impedances are encountered in the theory of waveguides. One is wave impedance, another is characteristic impedance. First one is useful in computing power flow through the guide, whereas second one is useful for providing impedance matching. Their values depend upon dimensions and modes. Now expressions and all that, they are considered derived under impedance characteristics. Attenuation. In the real world, zero and infinite conductivities are not achievable. As already mentioned, the hollow region is always lossy. It is not perfect. Similarly, the conductors are not perfect conductors. Walls are not perfect conductors. So, a certain amount of losses takes place, resulting in attenuation of the wave while it is traveling through the guide. How much attenuation it undergoes while it is traveling. That aspect is studied under attenuation. Attenuation has several components. Their components, their amounts are evaluated here. From the expressions of attenuation, measures to reduce the losses can be taken. This is the overall picture regarding the analysis, or it is bird's eye view of the waveguide theory, hollow pipe waveguide theory. Specific analysis or analysis specific to particular structure that is undertaken in the next coming sessions. Enough